Hi, I'm Scott Lacey, a fire protection engineer with a background in municipal and industrial firefighting, code development process, and AHJ, and as a consulting engineer. In this video, we're going to look at Section 6 of the Enhanced Rural Fire Water Regulations. Section 6 covers residential subdivisions with creditable hydrant protection. That's a term used in the ISO and insurance criteria. This training is intended as an overview of content within the regulations. Specific content wording in this video is subject to change with updates to the regulation. Refer to the latest regulations for the most current criteria. Here's an image of the table of contents for Section 6. The focus, as we indicated, of Section 6 is for a subdivision to satisfy the criteria for a creditable hydrant protection in accordance with ISO. Section 6 would apply when you do not have a municipal type water system for firefighting. As we discussed in previous videos, our preference is per Section 3 is that we have a municipal type water system with hydrants and potable water throughout the system under constant pressure. However, we recognize in many rural areas this may not be feasible due to the required pipe size for fire flows and the limited domestic usage for turnover. So if we're going to have wells on the properties or have small water lines just to serve domestic needs that cannot support the firefighting operations, we need to look at other options for firefighting, and Section 6 is the preferred criteria to satisfy this. Now, the objective is that all properties are to be within a single large diameter hose lay of a water source. ISO requires for credible hydrant protection that a water source be within 1,000 feet of the closest part of any structure. To ensure this, we have provided criteria within the regulation of 900 foot from the water source to the acceptable parking area. The acceptable parking area is generally 40 to 60 feet in front of the structure. The local jurisdiction may amend this and go with lower or shorter distances. An example would be if a rural department only carries 500 feet of hose on their truck, then they may reduce this down to 400 feet. The shorter distance is to ensure for the snaking of the hose and the connections at either end. Throughout the regulation, we generally refer to cisterns, but it is recognized in the regulation that other approved water sources may apply. The main reason we refer to cisterns is so they can be buried and not subject to freezing. An approved water source cannot be subject to freezing. Therefore, ponds, lakes, rivers, and swimming pools would generally not be an approved water source for the primary protection. Now, those sources are great and beneficial for firefighting, and there is criteria to use dry hydrants, such as in a large irrigation pond for a community or a golf course, but it is not going to be the primary if there's any possibility that it's going to be subject to freezing. The private hydrant system that would be provided under this, in accordance with NFPA 24, will be pressurized by the fire department. A single engine with a single driver can draft from the cistern source and pressurize the private main. This avoids hall studies and provides more boots on the ground at the fire scene, while also improving the ISO PPC ratings for the creditable hydrant protection. Now let's take a look at the site plan for the private hydrant concept. This is included in the regulation. Now in this example, we have a subdivision showing roads serving multiple parcel or lots. These lots may vary from an acre, half acre, 2.5, 5, 10 acres. So just a general concept here. And what you'll see is that in this case, we show at a high point elevation, we have cisterns, in this case 3 cisterns side by side. From those cisterns in the drafting point, the fire truck would pump into an inlet hydrant right adjacent to them which would pressurize a hydrant system throughout. Now, throughout this system, we look at, if we follow the 900-foot criteria, from a hydrant, the path the truck would follow up to an acceptable parking area shall not exceed 900 feet, or as the jurisdiction is otherwise established. Again, they may reduce this to 400 or 500, so per the jurisdiction. Once we get to the acceptable parking area, we need to be able to, with no more than 300 feet of handline hose, get around all parts of the structure and the adjacent structures. So if we have a shed out in the back field far away from here, if that shed can be contained by tank water, it does not have to be within the 900-foot lay. However, you still have to be able to get a truck with adequate water supply for that hazard within 300 feet. So that'll be determined by the AHJ and based on the conditions, whether it's going to be a brush truck or an engine truck. So we still have to have access to be able to get to that hazard, but if it can be handled by tank water, it does not have to be within the 900 foot or as determined by the AHJ from the hydrant. Other factors are going to include the elevations and slopes, and are there hills. So we indicated that in this example, we have the cisterns located at the highest point for this example. This could be level ground or this could be quite sloped. If we put the cisterns at a high point, then we have the potential for gravity feed, where these cisterns are automatically piped into this hydrant system. And we could potentially have pressure then at these hydrants without needing a drafting truck. So again, depending on the elevations, let's say this is a gradual slope downhill to this far end of the subdivision. We could potentially have 10 psi here, 15 psi here if it continues to slope. We could potentially have 40 psi at the hydrant at the far end without any trucks pressurizing here at the cistern point. So this is important to consider and figure out with elevations and how, if it goes down, if it goes up and it goes down. So different factors that need to be considered. But this will allow to potentially have more water even quicker rather than waiting for the additional engine to get here to be able to pressurize the main. Now in this example, we're looking closer at the cisterns. So in this case, we have three 30,000 gallon cisterns, which it's important to recognize that generally it is not feasible to transport or ship cisterns larger than 30,000 gallons. Although they are made larger and it is possible, 30,000 gallons is generally kind of a limit for the shipping of these down the hallway and what's required for the escorts and the roads they can get them on and the radiuses and the turns, especially in these rural areas. So that's an important factor to be considered in the design, is how are we going to get these cisterns to the source, as many times they will be shipped from out of state. So it's important to consider how you're going to get them there and then how you're going to get them around the roads for remote areas. Now in this particular case, we indicated we have the three cisterns. All three cisterns have the capability of being drafted from. All three have their own fill pipes. They have in this case, this is configured for gravity feed. So at the bottom of these cistern tanks underground, they have an 8-inch line with isolation valves that connects these. So each one has a street valve in the ground for isolation for maintenance. So at some point, these tanks are going to require internal inspections and maintenance. So the isolation valves allows for one of these tanks to be pumped out and drained for maintenance without necessarily taking out all the other tanks. So we need to make sure we allow provisions to do the maintenance on those. This far tank here, because we have three tanks, we exceed certain criteria within the regulation that the internal eductor is provided in this tank. So in the overview video, we talked about the eductors. So watch that, the introduction video. But in here, we would have an internal eductor that allows all of this water, since they're all connected together, That allows all of this water to be accessed by a truck that does not have hard suction. So it provides redundant means of getting water out of the tank, but it also can be used without any trucks, such as mutual aid trucks, that don't have hard suction, or if we have a leaky hard suction hose, or we've lost the gasket, or the gasket is dry rotted and cracked, we still have a way to get this water out of the system. Now in this configuration, we have criteria for 2 fire trucks to be able to pull off out of the main road to access these. So one truck could pull up first and be drafting, while the other truck could be connected to the adductor. It could be a tanker using to refill these if it's going to be a long operation, such as a wildfire mitigation or control for defensive operations. So the provisions are here for 2 trucks, up to 2 trucks, without blocking other emergency vehicle and access on this roadway. So in this case, this truck is connected to the hard suction. They are drafting out of the cistern, which again, these are all connected together. It goes through the pump, comes around, and immediately pressurizes back into the inlet hydrant. So the inlet hydrant has kind of reversed fittings on it to allow for the hoses to connect and push inward. In the regulation, this is identified as a black hydrant. So this hydrant would be black, flagging it as an inlet hydrant. We have other hydrants on this section that are served by this fire main. Those would be purple, as they are non-potable hydrants. So purple hydrants will be used for non-potable water. They will have color reflective bands on the hydrants, as well as snow poles by the same colors and color coordinated. So as an example, this hydrant may have a green reflective band on it, and the purple hydrants that are served by this inlet hydrant would also have green reflective bands to indicate that they're on the same zone. That's to help with coordination, that when the arriving truck first gets to the attack, to the house or the fire, when they lay a line, they radio to the other trucks or to dispatch that they're grabbing the hydrant on the green zone. That helps to ensure that when the truck gets here to the drafting hydrants, that they're on the same zone and the same hydrant. Because we could have another subdivision adjacent to this that maybe has its own cistern and its own private main, say phase 2 of this subdivision. Pumping into this hydrant may not serve the hydrants in that phase 2 part of the subdivision. So in that case, that's where the color bands and the color poles are critical to make sure that they're on the same zone. Now in this case, we also have a post indicator valve that's shown right here, adjacent to the hydrant. That would also be black. That is used to isolate these tanks. So normally that valve is open to allow these tanks to gravity feed through this system, assuming we have elevation to help us with the gravity feed, as discussed on the previous slide. So that allows all these tanks to have a positive pressure on the system. However, when the truck gets here and starts drafting and pressurizing this hydrant, there you have the potential of putting the water back into these tanks versus going down the line to the other fires. So once they establish a positive pressure flow into this hydrant, then this post indicator valve can be closed to isolate these tanks. Now you no longer have the gravity feed. You're totally relying on the truck to pressurize the line. Cracking this valve open slightly will allow some recirculation from the truck back into the tanks, so it can recirculate. That way, if the attack trucks are down the line as they open and close their lines or doing mop up and shut down for a little bit, you can still have some flow and pressure on their lines, but still be circulating water through the truck pump and back into the tanks. So this will become with operational training and understanding how the concept works, but how this could be utilized for cooling and recirculation of the water as well. This is a general concept of how these 3 cisterns, what they would look like from a cross-section view. So you'll notice that we have the gravity feed line we talked about here. There'd be an 8-inch line that would go out and then tie into the other tanks. This would also then tie into the underground main to feed the hydrants. So this would be used where we do have elevation in our favor and we're providing gravity feed to those other hydrants. If we were not taking advantage of elevation and gravity feed was not going to be beneficial, then a single tank would not have this, but multiple tanks would still have this configuration, as this is how the elevation and the water level is going to balance between the tanks. So even if we're not using gravity feed, where we have multiple tanks, a configuration like this would be appropriate so that as you're drafting from one tank, it is able to use the head pressure in the other tanks to come back in and refill this as we're drafting out here. Now in this case, we have the suction line. This suction line has to be sloped to ensure water drains back into the tank so we don't have trapped water for freezing, because if we did not slope this right, we have potential for freezing and breaking. In this case, we do have the internal eductor. That's what's shown here. If you did not have the internal eductor, this would just be piped down to the venturi plate. But in this case, since we are showing this tank with an internal eductor, there's another pressurized line that comes in to pressurize the venturi of the eductor. Now, it's also important to note that even though this tank has an internal eductor within it, it can still be used for drafting with a hard suction. So if you saw our orientation or the introduction video where we talked more about the eductors, you can do that with soft hose and get water out of this without a hard suction, or you can still use a hard suction here. Now, if you do use a hard suction on an eductor without pressurizing the line, understand that because of the venturi in here, there is going to be some restriction. So you do have to overcome that in the drafting, and you may not get quite as high a flow through this. However, if you take advantage of the pressurized line and you use hard suction and you pressurize this line, you're getting extra benefit. So you're getting benefit of the hard suction, drafting, as well as pressurizing this, and so you should be able to achieve over 1,000 GPM with the combination. The other pipe shown here, sloped back again, is the fill line. So that would be connected with a Siamese connection, kind of like an FDC or fire department connection on a building with clapper in it, so that you can either use one hose or two hoses to refill the cistern during an operation or in between or for maintenance. This shows the pressurized inlet and various fittings depending on the connections per the local HJ criteria. Something to note here is for higher elevations, altitude impacts lift. So when you're trying to draft at higher elevations, such as 5,000 feet, 8,000 feet, 12,000 feet, mountain areas, it is a lot harder. We have less atmospheric pressure pushing down on the surface of the water here. Therefore, it is harder for the truck to lift and draft out of these tanks. So what this concept shows is that we have criteria currently in the regulation to limit this lift to no more than 12 feet to the inlet to the pump, which means that this tank is going to be sub-buried. It's not going to be fully buried. What you do is you take the dirt out of the hole you dug for the tank and you end up mounding that over the tank to make sure you keep your frost depth, again, so you're not freezing the tank. But your road level is going to be lower than what the top of that mound is going to be. So that helps to reduce the lift to ensure you can get the most water you can out of this situation. Another thing to note is the slope of this pipe for the suction. We talked about how it has to be sloped for drainage. We also have to be careful that it is sloped upward, so as we're drafting, the air goes into the inlet of the pump. If you are to provide this drafting pipe up at high elevation, which I know some people want to do because they're worried about snow, they don't want this too low because it could get buried in the snow. The problem is if you try drafting from here with a hard suction down to the truck, what's going to happen is you're going to have air trapped in the high part here, and you'll have a very difficult time getting prime. And you've already got a challenge because of the lift. You're having come up with reduced pressure at elevations. But now you're trying to pull this slug of air down and into the pump. which will create a lot of challenges with prime. So we generally want this connection lower, even though snow is a factor. We want to make sure this slopes upward to the vent on the inlet of the pump. Here's a different perspective of kind of what the front of, in this case, that wall would look like, a means to have the fittings. So in this case, this tank has the internal eductor. So we have a pressurized 2.5-inch connection here, kind of like a single FDC, to pressurize the venturi. If you don't use that, that's fine. You don't have to use this. It just improves the water you're going to get out. This would be your dry hydrant connection. With or without an internal eductor, you'd go to this to draft from the tank. This would be your Siamese fill. You have appropriate signage indicating the cistern ID, the owner, phone numbers to contact, what area's protection, is it their addresses, is it single houses or a subdivision. So various signs as required and addressed in the regulation. If electronic monitoring is required, such as for a larger subdivision, the panel would be mounted here. Criteria for that with audio or visual alarms to indicate a low level. In this case, it's showing the post indicator valve adjacent to the inlet hydrant. This is what isolates your gravity feed. Once the truck starts pumping into the hydrant, this is where you would isolate so you're not pushing the water back into the tank. If you incorporate check valves to do this service, you have to be careful where that check valve is located and where it can be accessed. So that's an issue on the depth and how you're ever going to service or maintain or replace that. We do have a detail that shows if you want to do check valves with a gravity feed system where you can incorporate them into the tank. That way you could get into the tank to do maintenance on the check valves. The problem is that the tanks cannot equalize and balance themselves with check valves, because the check valve is literally going to stop the water from one tank from going back into the other tank. So you may think, well, why don't we just use check valves? Well, that's the challenge, and you have to be careful with how those check valves are installed if they're on the lines that are also balancing the levels in the various cisterns, where you have multiple cisterns connected. This hydrant shows one method of installing snow poles. The regulation addresses multiple ways, multiple types of poles, depending on the local jurisdiction. And we have various fittings, again, based on Appendix E for the local jurisdiction. Is it going to be threaded? Is it going to be storts? What type of fittings do we need? All the fittings on this hydrant need to be positioned or installed to allow pumping into the hydrant. So even the 2.5-inch hydrant would have inlets similar to an FDC that even potentially a brush truck or a smaller engine could pressurize in and put water into the system. So the 2.5-inch and the steamer connections all need to be configured for inlet pumping to this hydrant. And then we have no parking sign to make sure we don't have abandoned cars, and we follow your local criteria for sighting or towing if necessary if we end up with abandoned cars parked in front and blocking this. Now the water quantity for Section 6 and subdivisions is based on multiple principles, including per structure and per acreage. So the water supply is intended to protect multiple structures as well as wildland defensive operations for the subdivision. So again, keep in mind here that we have a large subdivision with multiple properties now that have to be protected. So the water quantity is going to be significantly higher than what we had for individual properties or individual property owners. So in this case, we need a lot more water, and we need a way to distribute that to different parts of the subdivision as well to do defensive operations in the event of wildland. Calculations allow for sprinkler reductions when the entire subdivision is sprinklered. So all the structures within the subdivision, that has to be addressed on how they're going to be sprinklered, and that all of them are sprinklered in order to apply sprinkler credits to the subdivision as a whole. We talked about that in some of the earlier videos, how sprinklers are great and they do save lives, but they are not intended to extinguish the fire, especially when residential properties are generally only partially sprinklered. So residential sprinklers are intended to get people out of the fire, Not necessarily, although we sometimes see benefits. When the fire starts in a sprinklered room, we will see tremendous benefits. But what happens if the fire starts in the attic or in a non-sprinkler garage? In that case, the sprinklers will not stop the fire. It will overrun the system, and you're still going to lose the house most likely. So again, it's important that we have water quickly to get on this fire and try to control and minimize the damage. So don't give away all your water in your sprinkler credits. Now, calculations also provide credits for low intensity fire mitigation versus little to no mitigation. So as part of the subdivision plan, it needs to be addressed on how the properties and the wildland interface is going to be mitigated. The trees kept away from the houses, no combustible wood decks, no combustible wood fences. The bushes are not against the house. All these are factors that need to be addressed, as well as the hardening of the structure. So we need to make sure how the hardening of the structure, such as wood decks, that the vents have screens on them to prevent embers from getting in. These are all factors that must be in place. And the mitigation needs to be in place before any building permits are issued. It's important to document all the criteria that the developer agreed to regarding mitigation and water quantities and the credits they took or did not take, so that if things change down the road, you have that to fall back on. If a developer committed to doing mitigation, but then once the developer is out of the project, the homeowners association fails to maintain that mitigation, that needs to be accounted for in the legal documents so that you can take action to go back on the homeowners association, just as an example, to get additional water or to provide the appropriate mitigation. So it's essential that in the deeds for all the properties that this is all recorded so each property owner understands. Now keep in mind, homeowners associations can change the rules to the homeowners associations, their codes, covenants, and restrictions by vote of the board. So if you're providing credits for these items need to be documented as part of the individual property in the deeds with the county, not just tied up in homeowners association rules that can be changed by the board. Now, when we look at table 6.4, so you notice in chapter 5 or section 5, it was table 5.4. So following with that, in table 6.4 is where we come up with water quantities that are necessary for the subdivision. But you'll notice some differences here. So in this case, we still need to establish what the area of the structures is going to be. We're still taking into account the encroachment as per NFPA 1142. So we're still looking at areas that are each floor level and roof line and the encroaching structures. Now in a subdivision, a lot of this is going to be hard to know offhand. So again, it's got to be addressed in the deed restrictions. So if the developer, say, is going to limit houses in, say, phase 1, they can't build a house with a total area exceeding 5,000 square feet. Okay, so we're going to put these smaller properties to limit up to 5,000 square feet. Here's the criteria that would apply to that: without sprinklers and with sprinklers. Okay, and it depends on the acreage, and we'll look at that in a second. But if they are not going to put any restrictions, let's say they're doing 10-acre lots and the developer does not want to put any size restrictions within the deed restrictions or what they can build, then we have greater than 15,000 square feet or not limited. So in this case, you would fall into this criteria, whether it's sprinklered or non-sprinklered. Okay. The blue is the sprinkler credits when all properties are sprinklered, and the black would be the non-sprinklered provisions. Okay. So this is something to look at where a jurisdiction could, or the developer could look at saying, okay, we're going to limit it to 5,000, or we're going to limit it to 15,000 square foot, or we're not going to place any limits on it. Then we get into the section over here for the acreage. So if we have up to 50 acres or up to 10 lots, this column would apply. 51 to 100 acres or 11 to 20 lots, this criteria applies. 101 to 200, and so on. So the different columns apply due to the area that's being protected, and a lot of this goes beyond just the structure protection, because we're getting into now the defensive operations, the having water to be able to protect the structures in a wildland event. If you're using this regulation in an area that is not subject to wildfire, at least not currently, keeping in mind that that could change in 10 to 20 years, you may revisit this and amend this for your area. That can either be done on our level with a regulation more focused towards your jurisdiction, or it could be done through Appendix E for local criteria. Now, it's important to also understand that these numbers are based on low intensity fire hazards, generally not heavily wooded areas. So a little bit different criteria and a different approach than we saw in Section 5 for individual properties, but there are additional requirements in Section 6. So if the property is going to be heavily wooded or not mitigated, then additional water per acre is required to be added to this table. So this table does not account for it, but there is criteria to add additional water to the properties by acre based on mitigation factors. Now, generally, the fire flow requirements for these private mains are going to be required to achieve a 1,000 GPM flow or 6-inch minimum mains. Now, this does not mean we're intending to flow 1,000 GPM at a house or at a particular property. This is through the main. So when the engineer is doing hydraulic calculations to evaluate flow requirements, they're going to look at different numbers of what's going through the main, serving all the hydrants in that area of the subdivision, versus the additional friction loss on hoses going from the hydrant up to the truck. So hydraulic calculations for the hose lays may use the lower flows, and in table 6.5 it will address that and kind of provide flows, what the required flow is based on the required amount of water for that individual structure. Friction loss through fire hose is extremely high. If you've never evaluated or done calculations, a lot of engineers are used to doing pipe calculations, but the friction loss through hose is considerably higher. So in Appendix A, we do have some criteria, a table of just a typical manufacturer's flow information. You can also verify with that particular fire authority, because this can make a huge difference whether you're using 4-inch or 5-inch hose, or if they only have 3-inch, as to what flows and how much friction loss you're going to lose from the hydrant up to the attack truck. That will also correlate with how long of a lay they're doing. Are they doing a 900-foot lay, or are they only allowing 500-foot lay? So it needs to be evaluated carefully. Now, in wildland defensive operations, we want to recognize that you may have different points. So you may have a high overall flow through the main. That's why the main has to carry the 1,000 GPM, but we may be breaking up the flow at multiple points along the main to serve the trucks. So if we are trying to do any calculations for wildland, we want to take that into account that, again, not all 1,000 GPM is necessarily assumed to be going out of one truck or one hose at the end of that hydrant. They'll likely be distributed at different points throughout the subdivision. So that can be part of the discussion with the authority having jurisdiction and the designer. Now, we're not going to go into detail, but it's important to let you know that Section 7 provides alternative levels of protection for subdivisions. Section 6 is the very strongly recommended and the generally required level of protection to achieve the creditable hydrant criteria of ISO and for insurance. It's important to understand that insurance has changed a lot through the years. And what we're having a lot of problems with is insurance companies are leaving states and leaving areas and not providing coverage because the risk is just too high. So it's very hard to get insurance. It's not as much a factor of what is your insurance rate going to be. It's whether you can even get insurance, or are you going to have multiple providers willing to insure and protect the property. We're seeing that in a lot of areas where they can't even get insurance, or if they get one, they're going to pay whatever that one provider wants to ask for because they have no other options. There's no competitive rates. So it's important to understand that water supply is a critical factor with the insurance industry to look at as far as risk level protection. But Section 7 does provide alternatives. However, it does not generally satisfy the insurance criteria for the credible hydrant solutions. So we have included it in the regulation, something you can look at. Generally in Section 7, you are not going to have the private fire mains. So if that becomes an issue, and maybe just due to the rocks or so, it's just not feasible to run the private mains, you're going to generally end up with more cisterns at a shorter spacing. So where a private main can serve 4,000 feet from one set of cisterns, you may have cisterns at closer spacing. So it's important to understand the differences and the trade-offs to use Section 7, but just know that there is alternatives. It's just not at all recommended due to insurance challenges. Again, the lack of the credible hydrants and the failure to satisfy ISO hydrant criteria and the source and spacing requirements is a key factor for new subdivisions. Hopefully you found this useful. It touches on Section 6, the general concepts. Please make sure you review the specific regulation for your jurisdiction and any specific criteria in Appendix E or variations that they may have made, such as hose lays, fittings, diameters, threads, thread types, those kind of factors. Please email us any questions or comments. Thanks for your time.